Hi, I'm Philip. Today I'll be covering device concepts, specifically tokamaks. So, why do we need to confine plasma? If we look at a plasma in the wild, so we're looking at the sun, we're looking at the solar corona, you'll see these magnetic field lines that'll loop around in the solar corona. What you notice is that there's this glowing structure in the magnetic field. So what's that? That's a plasma. The plasma is following these magnetic field loops as they loop around in the solar corona. So what we learned from this is that we can combine plasma with a magnetic field because plasma consists of positive and negative positive ions and negative electrons. So the goal of fusion is to maximize the fusion trip product. So we need some measure of how much fusion we're actually having. So what we use is the product of the temperature, density, and the confinement time. And this will essentially give us a metric for how good our fusion device is. And so as we saw in the solar corona, plasma followed magnetic field lines. And so how do we create a magnetic field line? Well, we can use a coil and run a current through it. And then the current induces a magnetic field. So if you remember solenoids, you have coils of wire and you're running a current through it, and then you have a magnetic field inside the solenoid. And so we can use this principle to create magnetic fields in our device, and then our plasma will follow our magnetic field lines. So how do we actually get to a tokamak? So we start off with the plasma. As we know, the plasma consists of positive ions and negative electrons. And so they follow the Lorentz force. And so if you have an electric field, you have a charge that follows the electric field. And if there's a magnetic field, we know that charged particles will feel a force perpendicular to both the magnetic field and the direction of the charged particle. And so if we look at it in terms of cross product, you'll see like QV cross V. And so the direction of the force is perpendicular to both of them. And so your particles will essentially gyrate around the magnetic field lines. And so you can see that in this picture. There's this gyro motion of this electron around the magnetic field line, and that's because the electron is essentially, you treat the magnetic field as going upward, the electron is coming in to the page, and so we have to the page and upward, and then you'll feel a force in this direction, so that it'll move around, or it'll feel, in this case, electrons, so it'll feel a force. And so essentially we can confine our plasma with these magnetic field lines. So you put the plasma in the magnetic field, and the plasma follows these magnetic fields. So if we're looking at a plasma in this case, we can essentially create a magnetic field that you can see in the bottom left with a series of coils. So this is similar to a solenoid. A solenoid is this linear device where you have a bunch of coils. And you end up generating this magnetic field. But now what if we connect the ends together? Now we get this torus, and you end up getting the magnetic field on the bottom left. And so now we can have this magnetic field that goes around, and our plasma is essentially following this magnetic field. But you end up getting drifts. So before we talked about drifts, one of the drifts that you end up getting is the Brad-B drift. So this is a drift caused by non-uniformity in your magnetic field. So you have some higher concentration, some higher strength region for your magnetic field and some lower strength region for your magnetic field. And so then you have a gradient in your magnetic field. And so in this case, we see that the strength is highest at the top and then lowest at the bottom. So now you have a gradient that points up from the lower field strength to the higher field strength. And so your lower radius or radius of gyration ends up being smaller at the top and larger at the bottom. So if you follow the electron around, you'll end up seeing a smaller loop at the top and then a larger loop at the bottom. And so what you end up getting is that you get a net velocity in the direction to the right. And so this is an example for an ion. So you'll see you have a smaller Larmor radius at the top, and then a larger Larmor radius at the bottom. And so you have a net velocity to the left. And so in an actual tokamak, you'll end up seeing these gradients in your magnetic field. So where your magnets are really close together, on the inward side of your tokamak, you'll have a very strong magnetic field, and then on the outward side where your coils are further apart, you'll have a weaker magnetic field. And so you get the same magnetic field gradient, and you end up getting the same drifts, except instead of left to right, you now have drifts upwards and downwards in your tokamak. So as you can see here, the ions will drift up, and then the electrons will drift down because of this gravity drift. And then if you're interested in the actual velocity itself, you'll see it at the top, where it says cross product between the magnetic field and the gradient of the magnetic field will give you the same direction. The ions move up, and then the electrons move down. And so what you essentially get is this polarization of your ions and electrons, and that generates an electric field. And then if you remember just from last time, the electric field also has a drift associated with it. So you have this E cross B drift, where you have an electric field downward, and now you have magnetic fields going into the page. And so now you have an electric field going into the page, and you end up getting a drift towards either the inward or outward side. And so in this case, you have electric field downward, and the magnetic field to the page, so now you have this cross B drift outward towards the outside of your tokamak. And so you can't just have straight field lines, because then you end up having these drifts. So your ions and electrons will essentially create this charge separation because of this gravity drift, and then that will create an electric field, which then creates this E cross B drift that drives your particles outward, out of your plasma. And so they don't stay confined. So how do we keep them confined? Well, we can introduce this twist in the magnetic field. So we call it the rotational transform, and it's essentially the average magnetic field rotation. And so you end up having, instead of these straight field lines going around, you have this twist, and so the plasma spends roughly the equal amount of time on the outward and inward side of tokamak. And so how do we actually generate this twist in the magnetic field? Well, in tokamaks, we drive a current in your plasma. So if you remember, our plasma is conductive, so you drive a current in it, and a current generates a magnetic field. So now you have a magnetic field going the short way around the tokamak. And you have this original toroidal magnetic field from your magnetic field coils, and then if you add them together, you end up getting this twisting magnetic field going around your tokamak. The other way to generate this twist is by actually twisting these magnetic field coils themselves. So instead of having planar magnetic field coils, we now twist them to generate this twist in our magnetic field, and that device is called accelerator. So this essentially shows that current was then produces a magnetic field, and then that magnetic field, along with the toroidal magnetic field, creates this twisting magnetic field. So the tokamak was originally proposed by Andrei Sakharov and Igor Tamm in the 1950s in Soviet Union. And the word tokamak comes from Russian. It's an acronym for toroidal chamber with magnetic coils. And so it's essentially this device that's like similar to a solenoid, but you're connecting the ends together. So you have this toroidal device, and the plasma stays confined within it. So on the bottom right is what we started with, this straight field line toroidal device. And then on the left is what we get after we add a current in our plasma. So now you have this magnetic field that goes the short way around the tokamak, called the toroidal direction. And we have our original toroidal field going the long way around the tokamak. Then you add them together, and you end up getting this twisting magnetic field. So let's talk a little bit about where tokamaks come from and the history of tokamaks. So in the 1920s and 30s, fusion and fission was first introduced. So you might recognize the famous equation E equals mc squared. So energy can come from a change in mass. And so if we have fission, generally there's a reduction in mass, and then you end up getting that loss of mass ends up converting to energy, and you have this output of energy. In fusion, you end up having a similar result where you have ions that come together and then fuse into another element, such as two hydrogens fusing into a helium, and then the helium has a lower mass than the two hydrogens combined, and the difference in mass is accounted for as the energy release. So in World War II was the demonstration of nuclear fission for the first time, and then in the late 40s and 50s, fusion was worked on, but it's secret. There was an international race primarily between the US and Soviet Union, but also the UK, and other places around the world to get a fusion product that worked. And then in the 1950s, the tokamak was introduced in the Soviet Union by Andrei Sakharov and Igor Tam. And similarly, in the US in the 1950s, around 1951, the Stellarator was produced by Lyman Spitzer in Princeton. And that was the US concept, which kind of combated against the Soviet concept, which was the tokamak. So the first tokamak was actually built in 1958. This was the tokamak T1, and there was the Russians that built this tokamak essentially showed that it was more efficient or could reach higher temperatures than the Stellarator that the American concept had. And so ultimately what ended up happening was this Atoms for Peace conference in 1958, where the US side showed its Stellarator concept and the Soviet Union side showed the tokamak concept. And together they decided to declassify fusion research so that fusion could be explored globally and information could be shared globally to effectively get a working fusion reactor. And so the initial predictions of when a fusion reactor was going to produce net fusion energy was very optimistic, span like 10 and 20 years. But then they realized in the early 1960s that fusion is a lot harder than they initially thought. In 1968, the Soviets announced that they achieved 1 keV in the T3 tokamak, which preceded the initial T1 tokamak. And a series of scientists from the UK went to verify their experiment. So they took a Thomson scattering device, which was very new at the time, and went over there and measured the temperature and realized that it actually was around 1 keV. And so from there, the US changed its method from the Stellarator to the tokamak, and they started exploring tokamaks at the same time as the Soviet Union was. And so if we look at the period from 1960s to today, we'll see that the majority of the devices are tokamaks. And you'll see that in red, you'll see T3, which we talked about already, and then you'll see some of these American fusion concepts. So TF4, Alpha 4A, JET is in the UK, TF2R was new version in the US, Alpha 4C was also in the US. And so there was this large production of tokamaks in the around the 80s, and a little bit before and after the 80s, which was predicted to be the best concept for a working fusion energy device. At the same time, the number of Stellarators that were produced was much lower. So if you look in green, there'll be the Stellarator concepts, and you'll see a Model C in around the 70s, and then in the 80s was W7A in Germany, and you'll see less Stellarators in general than Tokamaks. You'll also see in black these laser fusion devices. So lasers became more prominent, became more efficient, and at the time, the concept of using lasers to produce fusion came up, and you'll see that the highest energy output was through these fusion devices. And so on the y-axis, you'll see this triple product that we talked about before. And so the higher the triple product, the more energy produced by the device. So now let's talk a little bit more about tokamaks. So in tokamaks, you can have these magnetic field flux surfaces. So if you end up looking at a cross section of the magnetic field, you'll see, and you're looking at the vectors produced by the magnetic fields, you'll end up seeing these closed nested flux surfaces. So starting from the magnetic axis going outwards, you'll see these surfaces in your magnetic field. And so in order to actually determine the rotational transform of our device, we can use the safety factor Q, or sometimes you'll see the rotational transform iota, which is just 1/Q. And Q is essentially the number of toroidal transits over the number of colloidal transits. The toroidal transit is the long way around a tokamak, and the colloidal transit is the short way around a tokamak. And if you put the number of long ways that go around for one short way that goes around, you'll get the safety factor. So why do we care about nested flux surfaces? For each flux surface, the particles will ideally stay on the flux surfaces. In reality, there is transport between flux surfaces for particles, but there's sort of they roughly stay on the magnetic flux surfaces. Each flux surface is also has a constant pressure. So the pressure gradient is generally perpendicular to the flux surfaces. The pressure is a constant on a flux surface. And then you have current that you can essentially treat as this surface current on like each flux surface for simulations and such. And so the colloidal flux is constant on each of these flux surfaces, and that's why I call it flux. So the ultimate goal is to produce energy. And so one of the ways to quantify that is to use this Q, which is essentially just the power of fusion that comes out over the heating power. So if you think about it, the total amount of power that you're using to heat it should be less than the total amount of power used for fusion in order to get breakeven. So if you have Q greater than 1, that means the power from fusion is greater than the power for heating. And you have, at least in a scientific sense, a net energy arm. And so you'll see these Q values for the different tokamaks on the right, and you'll see that no tokamak that presently exists has achieved Q greater than 1. ITER is a device that's currently being built in France that is predicted to achieve Q greater than 1, but it has not yet been built or certain. So tokamaks are essentially this toroidal device. So it looks similar to a dope, but some of the tokamaks are a bit more compact. And so they look more like the core of an apple, and then the the white part of your apple is like the vacuum region of your tokamak. So you'll end up seeing devices like this. So there's a device down in Princeton, NSTX, that's essentially this more of a compact device with this compact vacuum region, and what essentially looks like the core of an apple in the center, which has your magnetic field coils. So this brings up the point of how do we compare these larger donuts to these like smaller donuts that are more like an apple. And so we use the aspect ratio, which is the major radius. So that's the distance from the center of the donut out to the magnetic axis versus the minor radius, which is the magnetic axis out to the wall. And so this ratio will essentially give us how compact or not compact the tokamak is. So you'll see that these are like really large donuts have very high aspect ratios, and these more compact, like apple-like tokamaks have small aspect ratios. So another metric that's often used when assessing different tokamaks is the fusion beta. So this is essentially your kinetic pressure. So think of like the pressure of gas. It's the pressure we're talking about over your magnetic. So your magnetic pressure is p squared over 2 mu naught, and it's essentially you can think of it analogous to kinetic pressure. That's the pressure from like the magnetic fields. Okay, so how do we actually shape the plasma? So we can have these colloidal magnetic coils that go essentially the long way around a tokamak. And if we drive a current in these coils, then we can actually elongate the flux surfaces that we were looking at before. And so now you'll see on the bottom left, instead of these circular flux surfaces, now we have these more elongated flux surfaces. And so we can essentially put a current in the direction of the plasma current to create this colloidal magnetic field. So that's a magnetic field that's along like the colloidal cross section, and then that will essentially elongate our surfaces. So let's take a closer look at the flux surfaces. So if we see at the center is the magnetic axis, And then as you move out, you'll end up getting to the last post-Fock surface. And so outside of this, you'll end up seeing the separatrix. And the special part of the separatrix is if we look towards the bottom, you'll see this X point. And the blue section is our diverger. And so the X point exists so that particles end up going into the diverger. And so these particles are essentially the fusion-born particles, like the alpha particles that we want to exhaust out of our plasma. And so we have this X point at the bottom so that particles exhaust into the diverger. And then when they go towards the X point, they're unlikely to stream upwards back towards the top of the Tokamak. And so that's this idea of like it's hard to swim upstream for the particles, so they end up going towards the X point and then stream out to the divergers. And so the divergers essentially can also get rid of impurities that we have in the plasma on top of like alpha particles. So if we have impurities from the wall or elsewhere, it'll divert into the diverger rather than staying in the plasma. So the elongation also increases the safety factor. Remember that the safety factor is how we measure our rotational transform. And the elongation also allows us to increase our plasma current. So there's various other coils in a diverger, in a tokamak. There'll be passive coils and active coils. So the passive coils essentially don't have a current driven in them, and the active coils do, like the solenoid or the toroidal field coils. So the passive coils can be used to mitigate vertical instabilities. So if you think about a general copper coil, if you change the magnetic flux going through the coil, that will drive a current in. So these passive coils work the same way, where the magnetic flux in the coil is changing, and then that will create a current that opposes that change of flux. And so these passive coils can essentially help mitigate vertical instabilities in the plasma. There's also a solenoid in the center of the tokamak. And so this is used to drive a current in the plasma. So you can ramp up your central solenoid, and that'll increase the flux going through your plasma. It will then drive a current in your plasma. And then as you're ramping it down, that also drives it. There's also other coils. You have 3D coils, diverger coils, in-vessel coils that are also used to mitigate different kind of smaller instabilities. And there's many other devices and diagnostics used in a tokamak. So some diagnostics that will be used to measure temperature and density of the tokamak. Yeah, there's other parts of the wall that will try to shield from neutrons and other problems in the tokamak. So let's take a look at a video of MAST, which is an experiment in the UK. So you'll see in the center this plasma. It'll have this like D shape that we were looking at before. If you look on the outside, you can visibly see the plasma better than the inside. That's because we're looking in the visible light spectrum. And so in the center, you have plasma that's hotter than it is in the edge. And so you can see the plasma on the edge, but you can't see the plasma inside. So that's a full shot from start to finish, and you saw the plasma essentially collapse a bit. So now let's look at another tokamak. So again, you'll see the plasma at the edge of the cross section settled over temperature than it is at the center. And then there's these sparks that you see going around. And those are essentially impurities coming from the wall or elsewhere that's entering our plasma and heating up. And so at the end, you end up seeing this like large event happening in the plasma, and that is a disruption. So you'll sometimes hear about disruptions in tokamaks. That's essentially this like sudden stop of the confinement of the plasma. So now we can look at this link, which will actually show you a demonstration of how you can kind of shape your tokamak. So if you look here, this is a virtual tokamak that you can design yourself. This is through the PPL website. And so on the right, you can actually see this cross section of a tokamak, and then you can kind of mess around with it. So you can change the elongation that we were talking about before, so you can get it really elongated or close to a circular cross section. We can change the triangularity of it. You'll see it go become more triangular, and you'll see negative triangularity. You go negative, and then you can change the major radius and minor radius of it. This is kind of a way to play around the tokamak. So now let's go back to what we were talking about before. We were talking about the rotational transform of a tokamak device or any toroidal plasma device. And so before we were talking about essentially driving a current in the plasma to create this rotational transform in our magnetic field. Well, another way to create a rotational transform in your magnetic field is to actually twist the toroidal coils themselves. So instead of them being these planar coils, you now have these twisted coils that look maybe a little funky, but they'll essentially produce a rotational transform without actually having to drive a current in your plasma. And so that mitigates some of like the current-driven instabilities that you find in tokamaks, but then it creates additional problems because now you have this additional degree of freedom that you're trying to optimize for. So it's much more complicated to design and much more complicated to build, so because you have these really twisted magnetic field coils. And so it's, in addition to being a physics problem, it also ends up being a very large engineering problem of trying to wind and produce these twisted magnetic field coils. So we'll learn more about these devices called stellarators next time. But let's take a look at current tokamaks that are out there. So the largest tokamak in the world that's currently being built is ITER. It's over 6 meters in a major radius. It's this massive tokamak. You can see the scale of it with the person down here, and then this whole machine is a tokamak. It's this massive international collaboration between 33 nations, and it's currently in the south of France. And they're currently building it, and it's expected to be active in the 2030s. So the main tokamak currently in the US is D3D. This is in Southern California, in San Diego, and it's operated by General Atomics. So yeah, it's the main tokamak being used in the US, and it's used to test a variety of physics problems and also material problems. There's a lot of like material science problems and diffusion devices, so it's also being used for that, and testing active control and several of the problems that are used to create an actual working diffusion device. It's also very flexible, so one of the recent campaigns has focused on working on negative triangularity. So we saw in that little demo that you can essentially flip the triangularity of your device. So now instead of this D shape, now you have this like negative D shape. But yeah, one of the advantages of D3D is that it's very flexible, and so you can essentially use negative triangularity experiment. So you'll see negative triangularity on the bottom left, with positive triangularity in red. There's also this smaller tokamak using high temperature superconductors that's being developed in Massachusetts by CFS, Commonwealth Fusion Systems. So essentially, this private company that's developing Spark, which uses high temperature superconductors. And so it lets it be much smaller with a very high magnetic field strength. And the aim of Spark is to be the first Q greater than 1 fusion system. So that's the first toroidal fusion system that has net energy hope. So there's a lot of topics that are currently being researched. One of them is negative triangularity, as I mentioned. High temperature superconductors like those being used in Spark. There's the fuel breeding problem. So essentially you have these neutrons that can hit a blanket and produce tritium, and you need tritium and deuterium to do your your fusion. And so there's a very small amount of tritium available in the world now. So these neutrons should hit this green blanket and produce tritium so that we can have a fuel cycle that essentially is self-sustaining. And then there's issues of tokamaks are inherently pulse powered. So if you're trying to get like a steady load, how do you create a steady load? So you might need to have large batteries that will store the energy from the tokamak. And then we're looking at different types of superconducting material so that you can build better magnets. And then there's other problems like material science problems that you want to create walls that can essentially withstand the high heat fluxes that can come from a tokamak or disruption in a tokamak. And so there's a variety of problems that have to be solved, going through fields like material science, mechanical engineering, chemical engineering. And so it's really like a large problem that encompasses many different fields. Thank you.